Hi, and welcome to our section on parallel processing. In the previous section, we created a text mode utility program and learned about several of Python's built-in packages. In this section, we're going to see how to use both the high-level concurrent.features package and the lower-level multiprocessing package to help us write parallel programs. Both are part of the Python standard library. In this video, we're focusing on concurrent.features, the more abstract and easier to use of the two packages. Our focus will be on the four main operations in concurrent features. We will then move on to the usage of future objects and end with the implications of the mechanism of data transfer between processes. Let's jump right in. Some programs are what we call CPU bound, which means that the primary factor which determines how long the program takes to complete its tasks is how fast the computer can run through its instructions. Interestingly, most programs that we use on a daily basis are not CPU bound. However, for those that are, we can often speed them up by breaking them into separate processes. On the screen right now on the left, we have a CPU-bound program. It has many things to do, represented by circles, and the speed of execution depends on how quickly the CPU can process. On the right, we have a program that is not CPU-bound, which means, most of the time, it is waiting for the execution. The processes can run simultaneously on different CPU cores, or even on completely separate CPUs. This has the net effect of increasing the number of program instructors executed per second, which means that CPU-bound programs run faster. In some programming languages, we could see the same benefit by running multiple threads for a single program. However, as I mentioned before, most programs are not CPU-bound, so the creators of Python have chosen to optimize Python's threading system for the common case, which has the side effect of making Python threads not very useful for improving the speed of CPU-bound programs. Besides, it's easier for the operating system to optimize the execution of multiple processes than multiple threads within a process. So even if threading were a viable option, multiple processes would be a better choice for a CPU-bound program. We've already seen one very low-level approach to launching a process and communicating with it in our discussion of the sub-process module. However, for cases where the reason we want to do that is because our program is broken up into a bunch of cooperative processes that work together, Python provides us with a couple of higher-level toolkits that make things easier. The more abstract of Python's parallel processing toolkits is called concurrent.features. The concurrent.features module is designed for programs that can be structured with one controlling process and several worker processes, where the controlling process hands out jobs to worker processes and then collects and collates the results. That's a fairly generic model, especially for CPU-bound programs. So, concurrent.features is as widely applicable as it is simple to use. And it is simple. The basic usage is to just import it, create a process pool executor object, and then call that object's map, or submit methods to send work to the worker processes. When we're completely done with the process pool executor, and we know we'll never need it again, we call its shutdown method, or allow the with statement to do it for us. The process pool executor will take care of all the twitchy little details of creating and communicating with the worker processes. When we call process pool executors, map, or submit methods, we're asking it to call a function with the given parameters. But we want that function call to happen inside a worker process. That has some implications that might not be obvious. First of all, it means that the function and its parameters need to be pickable, which is another way of saying that Python needs to know how to turn them into a byte string that it can send to the worker process. For functions, that basically means any function is okay unless it was defined within the body of another function. For the parameters, it means that most objects will work, but generators and a few other kinds of special object can't be passed. It's important to be aware that both the function and the parameters passed to it can easily bring along information we didn't intend to send when they get pickled for communication to the worker processes. If any of the objects we send to the process pool executor references other objects, those objects get pickled up and sent to. It's entirely possible to end up sending most of the state of our program. That's particularly worth noting when the function we're asking to run is a method of an object. If the function is a method of an object, the whole object will get pickled and sent to the worker process, which means that the function call will be happening with a copy of the original object as its self-parameter, not the original object. Second, the return value of the function is pickled and returned to the controlling process. All of the warnings about passing parameters to the called function apply to the return value too. So for example, the function can't return a generator object, and if the return value contains references to a bunch of objects, copies of them will end up being sent to the controlling process. Third, and finally, the concurrent futures code that's running in the worker processes needs to be able to import the modules that our original code was loaded from. That means that we may need to use the if name equals main trick to keep the worker processes from getting stuck running complete copies of our program when all they wanted to do was import the module and find the function we were asking to have run. We've already seen the map method of process pool executor in our example, but let's look a little closer. The map method takes a function as its first parameter. We can also pass it one or more iterables, which will be used to figure out the parameters for each call to the function. So if we ask the pool to map the foo function to the lists 1, 2, 3, and 4, 5, 6, the result is that foo will be called with 1 and 4 as its parameter, called again with 2 and 5 as its parameters, and called a third time with 3 and 6 as its parameters. There's no guarantee about which order those 3 calls will happen in, though. After all, they're likely to each run in different processes, and the relationship between process scheduling and wall clock time is partly dependent on unpredictable factors. The map method hides that fact by waiting for all the calls to finish and produce the results, then returning an iterator over those results in the proper order. Sometimes the map method is too simple. What if we want to handle the results as each worker produces them instead of waiting for all the workers to get done? What if we decide not to run the function after all? What if we want to run different functions in worker processes at the same time? For that matter, what if we want to pass keyword arguments to the function? We could do all that and more using the submit method. Each call to submit translates to a single call to the function that we pass as submit's first parameter. The rest of the parameters and keyword arguments we pass to submit are passed into the function after being sent to a worker process. So for each time we call submit, one worker process calls one function with one set of parameters. Submit does not wait for the worker process to finish running the function before returning. In fact, it doesn't even wait for the worker process to start running the function. And so, submit does not return the result of the called function. Instead, it returns a future object. Future object is in some sense an IOU for the result of the function. If we have a future object, we can use it to check whether the worker process has finished running the function to get the result returned by the function, or even to set up a callback that will be called when the function finally does finish running. We can even use the future object to remove the function call from the queue of jobs that should be shared out to the workers. The done and result methods of a future are the ones we'll use most often. The done method returns true if the job is done and false if it's not. A job is done if it was canceled, if it raised an exception, or if the job function has returned. The result method returns the return value of the job function if it completed successfully. If the job function raised an exception instead of returning a value, the worker process will catch the exception and hand it back to the controlling process as the result of the job. In this case, calling the result method will re-raise the exception so it can be handled properly. If we call the result method before the job function is done, the result method will wait for the job to complete before it returns. That can be very useful, but sometimes we don't want to wait indefinitely. If the job isn't done quickly, we want to go on and do something else for a while. In that case, all we have to do is pass the number of seconds we're willing to wait to the timeout parameter of the result method. If the timeout expires without a result being produced, a timeout error will be raised. There are a pair of functions in the concurrent.futures package that let us wait on several futures at once. They're called wait and as completed. The wait function waits until all of the futures are ready to deliver their results, or until a timeout expires. Then it returns a set of futures that are done and a set of futures that aren't. In contrast, the as completed function returns an iterator that produces futures one by one as they become ready to produce their results. In rare cases, the done and result methods of future and the wait and as completed functions of the concurrent futures package aren't sufficient to let a program process futures at the proper times. For those occasions, it's possible to have the future call a function when the result becomes available. We can do that by passing a function into the future's add_done callback method. The future will remember that function, and when the job function is done, the callback function will be called with the future object as its only parameter. The code in the callback function can then call the future's result method to get the return value or exception that the job produced. Take note that the callback function will always be called in the controlling process, but it might not be called in the same thread as the main part of the program. When we use add_done callback, we need to be careful of thread synchronization issues, which is a big reason to prefer wait or as completed when possible. Future objects also have a cancel method, which tries to tell the system that we don't want the call to happen after all. This is not guaranteed to work because if a worker process has already begun a job, that job is no longer cancelable. If the job connected to a future can't be canceled, the cancel method returns false. If the cancellation succeeded, the cancel method returns true. The concurrent futures module is perfectly suited to farming out computational tasks to multiple processes to take advantage of the CPU power of multi-core and multi-processor computers. The map, submit, wait, and as completed functions are usually all you need for that kind of task. If the program we need doesn't fit into the send out jobs and collect the results model, we're probably better off working at a somewhat lower level of abstraction. Multiprocessing module, which is the topic of the next video.